Let's talk about how to make computer software safe and secure. A computer program consists of a sequence of instructions which programmers carefully arrange in order to accomplish some task. These instructions can be complex, and crafting them is an exacting process, so we commonly package them into components which serve as larger building blocks. Programmers assemble these components into an application that, when launched, will follow the enclosed instructions faithfully. Every interaction with a program, like logging into an application, travels a unique path through the program's code and produces some result. The goal is for this program to compute all that its users want while behaving only as its programmers intend. In order to gain confidence in an application, developers must check the effect of each path through the program in order to confirm that the outcomes are consistent with the expectations. This process is called validation, and while there are several approaches to it, all are very complex because even simple programs can be used in many ways. Effective validation will expose defects which might let the program reach an unintended outcome. When a defect is found, developers can repair or replace the defective component, and validation will continue. However difficult it is to say all that we want from a program, it is even more difficult to characterize all behavior we do not want from it. Unwanted results may thus arise from our failing to anticipate one of the ways that an otherwise valid program could be misused. Developers are effective at designing around a potential misuse of a program once they know about it, so the ideal way to build confidence in the quality of our programs is to first characterize all goals in usable form, then check that all program execution paths are consistent with them. But that is only the ideal. All current validation methods leave gaps in the specification that may allow unwanted or unexpected output. And that brings us to intrusion detection. Intrusion detection refers to the practice of monitoring a program and its environment in order to recognize when some agent may be attempting to use it in some unintended and probably unauthorized way. We'd like not to have left our programs open to misuse in the first place, but as we said, that is so large a task that validation technology just can't do it yet. Intrusion detection is thus a sort of compromise that many developers make to sacrifice quality for more achievable and cost-effective protection. So far we've been talking about how difficult it is to validate and detect intrusions on a single system. But when multiple programs interoperate, they open vulnerable ports that hackers may use to gain unauthorized access to your program. The challenge and complexity of validation increases as more systems are connected to a network. When more machines are added, the functional surface of the system increases, as does the number of access points into the program. A hacker may scan random or even non-existent ports until it finds one that is open. In these larger systems, it is more difficult for the intruder to be detected. Even while monitoring this network and checking port scans for unusual activity, many exploits will go unnoticed until it is too late. Because this is often the case, many exploits are caught only after a program has been misused. Another problem is that when intrusion detection heuristics signal a possible misuse of your program, you might not be sure if the system has been compromised at all. Uncertainty about what a heuristic tells us is the reason a system administrator's most common response is to shut the system down. This is an understandably cautious move and buys time for the situation to be studied, but it brings a cost: complete loss of service. So what if we could be smarter in detecting intrusions and not lose full service of our system while evaluating suspicious behavior? This is where our research comes in. We're studying how dynamic reconfiguration technologies might improve a system's security. Dynamic reconfiguration refers to changing a program while it is running. You might update the implementation of a component, perhaps to use a more efficient algorithm or repair a defect. You might reassemble existing components in some different way, perhaps adding new ones or removing others. Or you might map those components onto the underlying host's resources in different ways, such as to migrate a component to run on another computer. If a programmer wants to update a long-running program that is midway through a computation, dynamic reconfiguration will allow them to quickly swap out the old code with a different implementation. Important data from the old component would be cached in the operating system and would then get mapped into the new one. The new component could be faster or more secure and would pick up exactly where the old computation left off. So how might dynamic reconfiguration networks help with security? First, adding dynamic reconfiguration functionality to a system means that the developer has very in-depth information about each of the components that comprise the system. We can use this detailed information for added intrusion detection by checking a component's data while it's being accessed by a system and to make sure that no unauthorized access is occurring. This obviously adds a slight overhead to the program, but one research goal is to find whether adding these application-specific checks can match or beat performance of a traditional system. When malicious behavior is suspected, one reconfiguration rule would be to simply keep changing the system's components between equivalent versions in order to maintain service for legitimate users, but disrupt any ability for the intruder to turn knowledge about one execution path into an exploit. Analyzing the pattern of attempted intrusions might reveal that some components indeed have paths which could be used in an exploit, so other automatic rules for changing a runtime configuration might isolate these components, flag them for repair, and then restore full service once they have been patched. The research goal here is to demonstrate how expressive these rules can be and to evaluate their effectiveness in helping a system shake off intrusion attempts.